Today we're going to be talking about recursive sequences. So let's start off with a few basic definitions. Here we have a basic sequence, A1, A2, A3, so on and so forth. Now, what happens if the difference between two consecutive terms is constant? In that case, we denote it as an arithmetic progression, or AP, and if we were to give that constant a name, say D, we can easily derive the general term for each an with some initial value a1. Now, instead of difference, what about the ratio being constant? In that case, we denote it as a geometric progression, or GP. And if we were to name that constant R, for example, we can also get a general term with some initial value a1. How about the sum of several consecutive terms? Well, we'll call this a partial sum, denoted by Sn, where we sum the first n terms. Given that we introduced AP and GP just now, here are the general forms of their partial sums. It's quite easy to derive, so we'll gloss over that for now. Clearly, there are far more types of recursive sequences, so just to name a few, here are 4 common recursive expressions you'll come across. Obviously, getting the general term for these are somewhat harder, so let's look at some methods to do that. For this, let's focus on the second expression. Let's divide both sides by p to the n plus 1. Well, why? It allows us to form a substitution. Here we can form a Bn and simplify our expression. Now we want to be able to express this in terms of B1, our initial value. The easiest and most obvious way to do it is just by using the formula we have, or in this case, applying it n times. So we apply it once, twice, and now it should be quite clear how to reduce this to B1. Remember to undo the substitution to get back to A. Prior to the MO lessons in school, recursive sequences were already covered in the CMO senior training, and it was conceptually introduced in IoT, so there's already a level of familiarity. However, learning about more advanced substitutions and trickery in school helped to sharpen those skills and let me gain more experience. Recursion can be confusing at times, but at the end of the day, it's quite satisfying. The first problem we're going to tackle will be from SMO Open 2019, Round 1, Question 10. Pause the video now if you have to. In this problem, we're already given a recursive expression, and if it looks familiar, that's because it's in the same form as the example from section 1. I'm not going to go through the Bn substitution for it, so let's quickly turn that into an expression in terms of a1. And let's get rid of the sigma. Now we sub in our value for a1 that's been given at the start, and we tidy up the expression a bit. Notice that it's equivalent to 2 times n plus 1 squared. So now that we have our general form, we can go back to our problem statement and sub that in. So at the bottom, we have an a squared minus b squared situation, which means we can perform partial fraction decomp and split it up. Now, if we write out a few terms, we notice that this is actually a telescoping sum, and every term but 1 and 1/2 gets killed. So in the end, we have 500 times 3/2, and we get our final answer of 750. Now, our next problem is also going to be an open round 1 problem, but instead from 2010. Once again, pause the video if you have to. Notice how on the right hand side we have an n plus 1 as the denominator, and it's quite annoying, so let's multiply by n plus 1 on both sides. Now, notice that on the left hand side and on the right hand side we have n times an. So on the left hand side you have n plus 1 times an plus 1, right hand side you have nan and n minus 1 times an minus 1. So that means we can form a substitution where we let Bn equal to n an. And now if we minus Bn from both sides, we get that Bn plus 1 minus Bn equals to Bn minus Bn minus 1, which implies that this is actually an arithmetic progression with a constant difference between two consecutive terms. So let's sub in our B1 and B2, and we can get our common difference. So let's just get the general term of Bn and sub back in n times an. Now divide both sides by n to get our general form for an, and we can easily solve for m as requested in the problem.